Hello and welcome everyone. I am Shivani Garg, Assistant Professor from IIMT University. In the previous few lectures of control system, we have studied about the basics of control system, block diagram representation of a system and signal flow graph representation of a system. In this lecture and next few lectures, we will be studying about the time response analysis of a system. So let's start today's lecture. So what is the motivation behind this particular analysis? So this analysis would help us to know the performance of control system for any kind of input. As we all know, in the previous lecture we have seen we have the transfer function of any system which is equal to the output upon input. So if we know what kind of input we are applying to the particular system, we can get the output response in time specifications. And the second objective is to design a control system which meets the desired response and control requirements. So if we want some desired response, we can do the time response analysis and then we can design any system. So this is the motivation for time response analysis and design specifications. So what is basically the time response analysis? It refers to the analysis of system performance in time, that is the study of evaluation of system variables, specifically output with respect to time. So we simply would have a transfer function in S domain and we will have an input in S domain, and then we can calculate the value of CS, and by taking the Laplace inverse transform we can get the value of CT. So with the value of CT, that is output in time response analysis, time state, we can get the performance analysis. So there are two common ways for analyzing the response of a system. First is the natural and forced response, and second is the transient response and steady state response. For every response, complete response of a system, it is given by both of these responses, that is natural and forced response or the transient and steady state response. So let's see what are these responses. So first one is the natural response. It is the zero input response, where we have not applied any external forces, with the system is giving output with its initial condition. For example, we have a series RLC circuit where inductance and capacitance have some stored current and voltage respectively. So we will have, if we do not apply any voltage or current externally, we get the output because of these initial conditions of inductor and current, and it is called a natural response. And forced response is when there is no initial condition, we have assumed that there is zero initial condition or zero state response, and we apply the external forces and then we get the output, which is, this is called the forced response. So for example, in series RLC circuit, if we do not have inductor do not have any initial current and voltage, capacitor does not have any voltage initial voltage, and we apply a voltage and current, external source of voltage current, and then what do we get the output, which is it is called the forced response. So total response of the system would be the forced response and the natural response. Next is transient response and steady state response. Transient response is that goes to the zero as time tends to be large. As time tends to infinity, it goes to zero. So this is called the transient time. This can be tied to any event that affects the equilibrium of a system, which can be switching, disturbance, change in input, or any kind of fault. So another is steady state response. This is denoted by YSS. It is the time response of a system after the transient practical vanishes and the time goes to infinity. So the overall in time response would be equal to YTR, which is a transient response, and YSS, which is a steady state response. Okay, so we have a combination transient total. Time response would be equal to transient response plus steady state response of a system. So we have some standard inputs. As we know, when we design a system, we do not know how what kind of input we are going to apply in the practical system. So for testing purpose, when we design the system, we apply some standard inputs to it to check what will be the performance of the system. So we have some standard inputs. So what are these inputs? These are unit impulse, unit step, ramp and parabolic. These are the 4 types of standard input signal. And why do we apply them? Because most of the systems, most of the inputs are characterized by these responses only. So if we apply these standard input signal to any system, we can observe that this system will respond in the same manner as we are designing at the designing purpose. So these inputs are chosen because they capture many of the possible variations that can occur in any arbitrary input signal. So what are these test signals? First one is the unit impulse signal. It is a signal which is non-zero only at t is equal to 0 and it integrates to 1. Okay, so in mathematically it can be represented at integration minus infinity to infinity delta t is equal to 1 or f of delta t is equal to 1. And in graphical representation it can be represented by, if this is t and this is delta t, this is minus 1, this is 0 and this is 1, then it is 1 at t is equal to 0 only. So this is the graphical representation of this particular signal for unit impulse signal. And the second one is unit step signal. It is a signal that switches to 1 at a time instant and stays there indefinitely. So for in mathematically it can be written as xt is equal to 1 for all t greater than 0 and xt is equal to 0 for all t less than 0, or f of xt would be equal to 1 by s. The Laplace transform of f of xt would be equal to 1 by s. So this can be, in graphical representation this can be written as, this is t and this is say xt and this is 1. So at t is equal to greater than 0 it is 1 and at t less than 0 it is equal to 0. So this is the unit step signal and this is the Laplace transform of unit step signal, which is equal to 1 by s. Third standard input signal is ramp signal. It is a signal which increases linearly with time, where xt is equal to, mathematically it can be represented at at for all t greater than 0 and 0 for all t less than 0. The Laplace transform of this particular signal is a by s square, and graphically it can be represented as, so if it is t, this is xt, then it is a straight line and with the slope a. Okay. Next is the parabolic signal. Parabolic signal is the signal which increases with time but at a rate a t square by 2 for all t greater than or equal to 0 and it would be equal to 0 for all t less than 0. The Laplace transform of this particular parabolic signal is a by s cube, and in terms of graphical representation it can be represented by, if it is t, it is xt, it is a parabolic curve. Okay. So these are the 4 standard input signal which can be applied to any system and we can get the response for that particular input signal. Okay. So let's see for first order system how these inputs are for first order system, how the first order system reacts with all these inputs. So this is the standard form of first order system, which is here Rs is the input and Ys is the output. Okay, so this is the forward path transfer function Gs and this is the feedback path transfer function Hs. So as we have studied in the previous lectures, the overall transfer function for this particular system would be equal to Ys upon Rs is equal to Gs upon 1 plus Gs Hs. So if we put these values in this equation, we get the transfer function Ys upon Rs is equal to 1 plus Rs plus 1. So here Rs is called the time constant which characterizes the speed of response of a system to any input. Higher is the time constant, you will get the slower response and vice versa. That is, if you have a small time response, you will get the speedy response, and if you have a higher time constant, you will get the slower response. So let's see this signal with different kinds of inputs. So first one is the first impulse response of first order system with impulse input. So as we know that Laplace transform of impulse input is, which is equal to del t is equal to minus infinity to infinity is equal to 1. That is the Laplace transform of this particular system is Rs is equal to 1, and we have we already have Ys upon Rs is equal to 1 upon Rs plus 1, the transfer function. So from here we have Ys is equal to Rs plus 1 into Rs, and if we put the value of Rs, we get Ys is equal to 1 upon Rs plus 1, and then we take the inverse Laplace transform of y. Then we have this inverse Laplace transform of Ys would be equal to the inverse Laplace transform of this, which is equal to 1 by r e to the power minus t by c. T by r. Okay, so r is the time constant of the system. It is called the time constant. 1 by r e to the power minus t by r is the transient term of ytr. The steady state term SST is equal to 0, as this term would become 0 as t tends to infinity. So this is our transient response, and for this particular system the steady state response is 0. So if we draw the graphical representation, we have this is yt and rt. Okay, so this is your rt, this is 1, okay, and this is 0, this is minus 1, and this is 1. So at t is greater than 0, for t is equal to 0, this is t is equal to 0. For t is equal to 0, it would become, for t is equal to 0, it would become 1 by r, and for infinity it would become 0. So this is the time response for this particular system in graphical representation and in mathematical representation. So next is the unit response for the first order system. So our unit response is equal to 1 for t is greater than equal to 0 and 0 for t is less than 0. The Laplace transform for this is 1 by s. So again we have Ys is equal to 1 by Rs plus 1 into Rs. If we put the value of Rs from here to here, we get 1 upon s Rs plus 1. So if we do the partial fraction of this particular equation, we get 1 by s minus r upon Rs plus 1. Now we take the inverse Laplace transform. Yt is equal to Laplace inverse of 1 by, it would get, we will get 1 minus e to the power minus t by r. So if we see in this, we have for when yt is equal to 1 minus e to the power minus t by r, and for limit t tends to infinity, yt would be equal to yss. This would be equal to 1. Okay, so this is your steady state response, and this is your transient response. In this case, transient response is equal to e is equal to minus t by r, and TSS is equal to 1. So if we draw the graph, so we have t, we have this yt, this is 1 and this is say rt. Okay, so what we get yt at t is equal to 0, this is 0. So at t is equal to 0, this would become 0. So we have a value 1. At t is equal to infinity, this would become, so this is rt at when we calculate yt. So at t is equal to 0, if we put t is equal to 0, this would become 1 and this would become 0. So this at t is equal to 0, this would be 0, and at t is equal to infinity, this term becomes 0 and this becomes 1. So we get the time response this. So if this say this is for r1 and this is for r2, so where r1 is less than r2. So if we increase the time response, we get a slower response, we get at this point. Okay, so let's see for the next response. So next is the ramp input. For ramp input, so as we know what is ramp input is a straight line, RT is equal to T, then the Laplace transform of RT would be equal to RS is 1 by S square. Okay, so we have assumed A is equal to 1 here. So now Ys is, as we know, Ys is equal to RS plus 1 plus RS. If we put the value of RS as 1 by S square in this, we get 1 upon S square RS plus 1. Then again we take the partial fraction, we get 1 by S square minus R by S plus R square by RS plus 1. Then we take the Laplace inverse transform, we get T minus R plus R e to the power minus T by R. Okay. So this is the time response of first order system with respect to the ramp input. So here if we see from this point, for at t is equal to 0, this term, at t is equal to infinity, this term would get vanished. So this is our transient response. So this is our transient response which would become 0 at t is equal to infinity, and our steady state response would be equal to t minus r. So if we draw the graphical representation, we have this yt, say this is your RT or input. Okay, so if we draw this at t is equal to 0, this would become 1, this is R. Okay, at t is equal to 0, so y0 would be equal to 0 minus R plus R e to the power 0, which is equal to 1. So this would cancel out and this would be equal to 0. So at t is equal to 0, the response would start from here, and at t is equal to infinity, this term would become 0 and at this would become infinity. Okay, so we will get an output like this. So say this is for R1, R is equal to R1, in for R2, where R1 is greater than, R1 is less than R2. We will get this R1, this is the faster response, so R1 is less than R2. Okay. So next is for unit parabolic system. As we know, unit parabolic input RT is equal to t square by 2. The Laplace transform of this would be equal to RS is equal to 1 by S cube. We already have a transfer function for first order system, Ys is equal to 1 upon RS plus 1 into RS. So from here if we put the value of RS, then we get 1 upon S cube RS plus 1. Again we take the partial fraction, we get 1 upon S cube minus R upon S square plus R square upon S minus R cube upon RS plus 1. If we take the inverse Laplace transform of this particular equation, we get for 1 upon S cube we get t square by 2. For R upon S square we get minus RT plus R square by S we get R square. For R cube upon RS we get R square t e to the power minus t by R. So here if we see, this response would get vanished at t is equal to infinity, this would become 0. So here this is called the transient response, R square e to the power minus t by R, and the steady state response would be equal to t square upon 2 minus RT plus R square. So if we draw, we get, this is say RT, this is T. So at t is equal to 0, this term would become 0 and this would also cancel out, so it will start from 0, and at t is equal to infinity we have some error, so this would follow like this. Okay, so this is your yt. Okay, so this is the parabolic response for the first order system. So in this lecture we have studied about the time response analysis for first order system. In next lecture we will be studying about the time response analysis for second order system. So that's it for today's lecture. Thank you.